and second derivative function
Okay.
from the graph of the function means, as I told you already, when we take the first derivative of a function, we get another function, and if we take the derivative of the first derivative again, if we apply the differentiation on that, we will again get another derivative, which is again be a function. Then what will happen? We will be given with a curve, okay, and from that curve we have to graph the first derivative and the second derivative by applying the things, or by using the results that we are already done with. So initially, let's recall some basic concepts that are, I think, we need to first know, or we need to recall them before starting.
Okay.
So, for example, let's say this is our xy plane, um, this is x-axis, this is y-axis, okay. And for example, if you are having a function like just like this, yeah, and this is a good function. So this is a point, I named it A, and there is another point, I named that point B, and there is another point, I named that point C. Okay.
Okay.
Now, as you can see from the graph of the function, that the point A and point A and point C, they are local maximums, right? And the point C is is also a global maximum, right?
Yes.
And then the point B is our local minimum, and as we move forward, the global minimum of the function is approaching to is negative, right? Because the function is
Yeah.
moving downward, so it will approach to negative, right? Now there is a question that let's formally have the definition of how we can define global minimum or maximum. So I will write only for one, and with the help of that we will understand the other one. So global maximum or minimum. It's important to write the letter or.
Okay.
So the global
There is
maximum
no
or
global minimum for this, right?
the global minimum is approaching to negative infinity because it is decreasing, it is going downward from this end and also from this end, so it is going to negative infinity. So the global maximum of a function, the global maximum or minimum of the function is the greatest this is for global maximum or the smallest or the least
Okay.
value of the function that function it attains in the domain of the function, right? In its domain.
Yeah.
Okay. Then for finding the local maximum and the local minimum, we worked on a test which was particularly based on we can call it our first derivative test. Okay, what it is? What is our
First
first?
derivative.
Yeah, based on the first derivative, we can find the local maximum and local minimum, and also we can find out the interval in which the function is increasing or decreasing. So first of all, uh, we are taking the domain for an open interval AB, okay, and we know that the function has a turning point at x is equals to c. At some point in the domain, we will call it the turning point, such that there is a condition on point C that it is between the domain points. It is between this open interval A and B. Okay, we will call it if and
Yeah.
only if at that point the first derivative will become equals to 0. What does that mean? That means when I will take the first derivative of that function, I will get again another function, okay, and when I substitute that value, so in easy words I can say that if I make the tangent at that point, it would be parallel to x-axis. I am making the tangent at the point B and I am making the tangent at the point C. So now you can see the tangent line that I am making on the local maximum, local minimum, or global maximum or minimum. All the points they are parallel to x-axis, right?
No, not this, sir.
Yeah, this is not because it is not the global or local minimum because the function is moving still downward. Okay, it is still moving
Okay.
downward, so it is not the local or global minimum. Now, at these points, you can see that they are parallel to all the turning points. When I make the tangent on these points, we got a tangent line which is parallel to x-axis, and if the line is parallel to x-axis, that means its slope will be 0, right? If a line is
Yes.
parallel to x-axis, its slope is 0. So I'm writing m for this because we are quite familiar with that notation. So its slope is 0. So that's what I did here. I take the first derivative, I put the value c at that point, so I will get it is equals to 0. So how we were finding the turning points? What we were doing, we were taking the first derivative of the function, we were uh, equating the first derivative equals to 0, then we were finding the values of x, and then we were saying that they are going to be our turning points, right?
Yeah.
Okay. Now this is also very clear that on these turning points, on the points where we are getting the derivative 0, we will get our um, local maximum or the local minimum. Then how we can find out our local maximum? So for this one, we said if the derivative of the function is greater than 0. Now let me explain you first graphically. If I look at this point, okay, and I make the tangent line on this point, you can see this tangent line has a positive slope, right?
Yes.
So what is the
Positive.
characteristic? Yeah, its slope is positive. So what is the characteristic of this point? This point is on the left side of our turning point, right? I am naming the turning point to be C. So when I take the point on the left side of the of that turning point, and the derivative of the function at that point, it was greater than 0. So that means I will write the condition like x. What was my choice of x? That x was on the left side of C. Is it clear? Is it clear?
Yeah.
Okay. And what is the second condition? That when I will take the point on the right side of that turning point, so what will happen if you look at its slope? It is going downward, right? So, and we will say f prime of x is lesser than 0, okay? And what is our choice for x now? If x is on the right side of C, okay, then we will say then the function f will have then f is then f has local maximum at the point C at x is equals to C. Is it clear? This is the first derivative
Yeah.
conditions that on which we are already worked. Now, if you look at the local minimum, if when I will take the point to the left side of this point, you can see that the tangent line, the tangent at that point is going downward or it is decreasing. That means if I can write the second condition, that if um, f prime of x is lesser than 0 for x being on the left side of C, and if I take the point on the right side and I make the tangent line, you can see it is increasing, right? So the second condition would be f prime of x is greater than 0 for x being on the right side of C. Then we will say f has local minimum at the point x is equals to C. Is there any confusion?
No, sir.
Okay. Now, let me remove these tables. Just remove these. this one, this, not this one. Okay, I think it's enough now. If I remove further, I will remove the curve. Alright. Now, I'm starting from this point. I'm naming it point A, small a, and I'm naming this point where I was getting the point B, small b. Okay, so as
Yeah.
you can see, what is the trend of the function in this part? It is decreasing, right? What I will do
Okay.
if I take, if at any point, if at any point I make it tangent at this point, at this point, even at this point, what I will get? I'm getting negative tangent line, right? Its slope will be negative, right?
Okay.
So what we will say about the decreasing function, we will say that if f prime of x is less than 0 for all x and we are taking them in the interval. I took them in from the interval from one turning point to another turning point, okay, or maybe from the starting point to another point. So let's take them open, because I didn't if I take them on the point A and point B, I will get it equals to 0. Okay, then f is decreasing on the open interval AB. Is it clear?
Okay. And then it's increasing again.
I think, look, because the function is defined on the endpoints also, so I will choose not open, I will choose the closed interval. Okay, so I will choose the
Huh?
closed
What
interval.
is that?
Yeah, I said because if you look, the function is also defined at the point A, it is also defined at the point B, okay?
Yes.
And there is another condition that whenever we are taking the derivative of the function, we cannot take it at the endpoints of the function. Why? Because at the endpoints of the function, there is no there is no condition, or we cannot set that the function is going to be the continuous. Okay. For example,
Okay.
uh, let's see if we have a function from this point A to B. This is B, and let's say there is a function from this point to this point, and it's been designed by some this way. Okay, and I have to check its derivative at this point, right? So first of all, how can I say that the function is continuous at that point, right? Because what I have to do at this endpoint, when we are calculating the derivative of the function, we will take b plus some h, delta h minus f of b, if you remember the definition, over delta h, and the limit was delta h tends to 0, right? So now at
Okay.
this part is not been defined for the function. Means if I add any step size in b, so at this point the function is not been defined. Sorry. Okay. So that's why we cannot calculate the derivative at the endpoints. Clear? Similarly, if I take
Okay.
delta h negative, I cannot calculate the derivative at the left point. Clear? So that's why whenever we are calculating the
Yes.
derivative, we are taking the open intervals. So, by the way, move to the main point that we were doing. Okay, now the points, if f prime of x is greater than 0 for all x belongs to a and b, then we will say f is increasing on the interval a to b. Is it clear?
Yes.
Just look at these points for a moment. We will use all these points when we have to graph the first derivative with the help of these conditions. With the help of these conditions, we will uh, we will try to graph the first derivative of the function. Just look at them. Take one moment. Take a moment. Yeah.
Okay.
Now, what are the key points? The key point is that now let me try to write the some equivalent results to these points. Uh, I can say that at from this point, I'm writing it in an equivalent way. At turning point of f, when the function is changing from increasing to decreasing or decreasing to increasing, what we will get? We will get f prime of, at turning point of f prime is 0. Can I say that?
Yes.
So that means when I will um, try to graph the first derivative of the given function, so at its turning point, I will the turning points of the given function will be the zeros of the first derivative. Is it clear?
Yeah.
Okay. Now just keep that property in your mind. Come up to this question. So at the turning
Okay.
points, let me write the condition first. At turning points of the function of f, then I think it's just better to write it in a different way. Turning points of f are zeros of f prime. Is it clear? I think you will have no objection on that, right?
Yes.
Okay, so by keeping that property in your mind, let's change the color to the green one. Okay, so what are the turning points? This point is the turning point. This point is the turning point. This one is also the turning point, right? This point
Yes.
approximately, then this point. All of them are the turning points of the given function, right? So at these points, what will be the condition on the derivative? That these are the zeros of the derivative, right? So at this point, I will get the 0 of the derivative. Now with the green, I am trying to graph the first derivative. Clear?
Okay.
At this turning point, I will get the 0 of the derivative. Clear? At this turning point,
Okay.
again I will get the 0. Is it clear? Similarly,
Yeah.
at this point x, I will get the, if I consider this point as my turning point, so I will get 0 here and I will get 0 at this point. I believe that I made all of them correct. Is there any confusion in this step? Is it clear?
Yeah. No,
Okay.
no, nothing is confusing, sir.
Okay, good. Now look at this property. Yeah, this property. The points, I will write again the converse of this statement. If f prime of x is less than 0, we will say f is decreasing, right? So equivalently, I can write that all the points in which function is decreasing, all the points in which function is decreasing, f, the derivative of the function will be negative, right? So I am
Yeah.
naming it with the help of the interval. So I can say that similarly, the interval in which the function is increasing, the first derivative will be greater than 0, right?
Yeah.
Okay, so I can say that the interval in which f is increasing or decreasing, uh, that will tell us that the graph of f prime is positive, right?
Yeah.
Or just let me just reload my console. Let's go. Negative. Is it clear? So the points at which
Yeah.
the interval in f, the function is increasing, the graph will be positive, and the interval in which the function is decreasing, the graph will be negative. Is it clear?
Yeah.
Okay. Now there is a question. Obviously, if you look at this function from the number of rows, I think we can guess the degree of the function 1, 2, 3, 4, 5, 6. This function has 6 rows, or its degree will be 6, the function that is being graphed here, right? So now we will get when we will take its derivative, first derivative, its degree will reduced by 1. So its first derivative will have 5 rows, and I think we graph 1, 2, 3, 4, 5 rows. So if we are graphing a function of degree 5, obviously we will get the turning point in that one also, right?
Yeah.
So now there is a very obvious question that what would be the turning points of f prime. So if I am going to graph the function f prime, so now there is a question that what points would be the turning points of the f derivative. Is the question is clear?
Yes.
Okay. So now to answer this,
Basically, we have to find the first derivative to find the global maximum minimum, and then the second derivative to find the local maximum minimum.
no, no. Now our target is not that. What is our target? Our target is that we are given with the function. Okay. Yesterday, I think on the graphing calculator, we worked on
GeoGebra.
yeah GeoGebra. we worked on what would be the derivative of the function, and I think you were uh, we looked at that it would be again a function, right? At some kind of a function, right? So that's what we are looking for.
Okay. Okay.
We are looking that what kind of a function will be its derivative. Obviously, it would be a function, but what kind of a function? Okay, so now we are done with
Okay.
two steps. We are struggling with the third step, and our question is at what points, what would be the turning points of the first derivative? Is it clear?
Yeah.
So, from the all the things that I wrote, all the points that I wrote here, we can get the turning points of the function from the first derivative, but still we are unable to get the turning points of the first derivative. We can get the turning points, we can find the local maximum, local minimum with the help of the first derivative. But graphically, there is another point which we were saying, the point of inflation, right? So that point will help us to find the turning point of the function. Okay. So to discuss
Yeah.
to discuss that, we will take help from the second derivative. So let's try to write the conditions for the second derivative. Okay. So for example,
Yeah.
what is the condition for the second derivative test? Now I am writing the second derivative test. Okay. So what is our second derivative test? Okay. Second derivative test. What it says? It says that um, number one, if we are getting our turning point C, if f prime of C is 0, and if we calculate the second derivative at the point C and it is less than 0, then the function will have the local maximum. Then f
Yeah.
will have local maximum at the point C, right? And the second condition,
Yeah.
what was the second condition? If the first derivative is 0 at some point C and f double prime of C is greater than 0, then um, f will have local minimum at the point C. Is it clear?
Okay. Okay.
Okay. Now there is another possibility that on a point there is a point when I take its first derivative it was 0, and at that point its second derivative also becomes 0, right? Then what
Yeah.
would be, then what we will say, then the second derivative will become, the second derivative test will become inconclusive. So second derivative test will become inconclusive. Okay, and to solve
Okay.
the problems, we will move to the first derivative test for the local extremas or for the local maximum or for the local minimum. Is it clear?
Yes.
Okay, now there is third point, a third definition for the point of inflation. So how we will define that?
point of inflection.
Yeah.
A point where there's a change gradient.
The point, the change in the concavity, right?
Yes.
So the point at which the gradient will change. So now keep it in your mind. What is gradient? Gradient can be obtained by the first derivative, right? So let me write its definition. So we will say if the function f its changes the concavity at some point c in the interval, obviously open interval a and b, then the point c f of c is point of inflection. Okay, now what is its properties? What are its properties? Point of inflection is a point in which the function will change its concavity. Concavity means what is it? No, okay, I have a question.
Yeah.
What is the difference between concavity? We say function is concave up, concave down. We were discussing about that. So how can you distinguish between a function is concave up and a function is increasing? What is the difference between increasing function and a concave up function?
So what's the difference between?
What is the difference between increasing interval and concave up?
Increasing interval
Mhm.
increases. It can be from a decreasing point or to a decreasing point. But then concave up is it's just specifically from a decreasing point.
What is
This can
yeah,
be
yeah.
increasing. This can
Mhm.
be increasing, but this is the concave up.
So what it describe? Can you tell me the graphically something more?
Hmm. Maybe I'll graph a sample function.
Mhm.
It's literally an M. Okay. So
Now
this is concave
wait
up
wait 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 wait
because
wait wait
it's
wait wait wait.
curving up.
The function
Yeah.
the function that you made is not differentiable at this point. Do you remember I
Yes.
told you that result? That if we are getting the sharp edges in a function, then the function we will say it is not differentiable at that point. So try to make another function.
Yeah. Okay, that's the function. So when the concavity changes from down to
Hmm.
up, that's called concave up. But
Okay,
then this can also be like
so cup shape curve,
what's
right?
the other word? Yes.
Concave up and concave down.
This is also when the function's going increasing. This is increasing function, but then this is not concave up because it's from infinity.
No, if you look at the behavior at this point, the function is moving from this to this, so it is concave down. At this point, the function is moving from this to this. Okay, so it is concave up.
Yeah.
Okay, if a function is concave up, what we know from the second derivative about that?
Second derivative will be
Yeah,
also of gradient.
the second derivative will be positive, right?
Yes.
If the function is concave up, at a point at which the function is concave up, we will say its second derivative is positive. Okay.
Okay.
Yeah. And keep it in your mind at, okay, if second derivative of the functions is greater than 0, then we will say, let's take an interval. Open interval, let's say, yeah, it would be better if we take the open interval a to b. Okay. Then f is k up in all the points. Okay, on all the points, on all those x. Okay.
Yeah.
And if similarly we can write it for concave down. So if f double prime of x is lesser than 0 for all x belongs to a to b, then we will say f is concave down. Okay, is it clear?
Okay. Yeah. Clear, sir.
Okay, now if c is the point of inflection, then what would be its derivative, its second derivative at that point?
It should be negative, right?
Why?
To start going negative.
From where we get the definition of the, we said that it is changing its concavity, and concavity means function is increasing from positive to negative or from negative to positive, right? So its slope is changing. You can see
Yes.
its slope is changing from positive slope to it turns into negative slope. So if we are talking about the slope, that means the first derivative will change its sign. It will change from positive to negative, right?
Yes.
So if the function's first derivative is changing its sign at some point, for example, I'm not pretty sure what would be, but I know that at this at this turning point, the function's first derivative will be 0. It is increasing in this interval. So maybe kind of this function we are going to get. Okay, so what will be at the point of inflation? This is the point of inflection. The concavity will become, the second derivative will be 0. Okay, so at point of inflection,
Okay.
the second derivative at c, if it is 0, then we will say c is point of so now this is very clear that at the point of inflation, okay, at the point of inflection,
Inflection.
yeah, the function, mm, its second derivative will be 0. That means this is the turning point for the first derivative. Now let me tell you how to find that point. It's been very interesting and very easy. let's take the function that you consider this is their first. Okay, so between these 2 points between these 2 points in the middle we will get point of or inflection. Okay, I saw this word and this word also for this thing. Okay, so the point of inflection
Yes.
is between them. Clear? Is it clear? So I ask you a question here, that what would be the turning point of f prime? So it would be at point of inflection, or you can say is it clear? Is it clear?
Yes.
Okay, so if all these things are clear, then I think we are ready to graph the function. Now keep it in your mind that the turning points will be at point of inflection. Okay. Now, as you can see, sorry, where we were to, yeah, this one. So where would be the turning point? The turning point will be at the point of inflection, and the point of inflection, I am highlighting the point of inflection on this curve with kind of this color. Okay, this would be the point of inflection approximately, because it is between the turning points in the middle. Okay, and from this turning point to this turning point we can assume that approximately this point is approximately at the point of inflection. We will get the point of inflection at this point. As I told you, where would we will get the point of inflection? Clear?
Yes.
And then um, similarly from this to this we will get approximately at this point, and the point of inflection obviously it will change on their corresponding x values. So these are the points where we will get the turning point of the function, the derivative. So this point. Is it clear?
Yes.
Okay. Now if all the things are clear, I think we are ready to graph the function. Okay. So let's see now.
Okay.
From this turning point to this point of inflection, the function is it is decreasing, right? It is decreasing, right? From this green point to this yellow point, the function is decreasing. Is it clear?
Yes.
And if the function is decreasing in that interval, if the function is decreasing in that interval, and we will get the point of inflection at that point. That's why I mentioned this one. Though it is decreasing from this to this. So if it is decreasing, then what we will get? We will get a, what we said? We said that if the function, the interval in f is increasing, the graph of f prime is positive, and in which it is decreasing, it would be negative. If it is negative, it would be obviously below the x-axis, right? So I will get a curve like this, a negative points. Okay, I take the f derivative lesser than 0, and particularly again for this interval, I will get the point of inflection at this point, the turning point for the derivative, and then some kind of this thing. Is it clear? Was from this to this part, the function was decreasing, and I will get the negative values for the first derivative by taking the turning point at this yellow point. Is it clear?
Okay.
Got it?
Yes.
Okay, now from this point to this point, the function is increasing, right?
Yeah.
So the function, its derivative will be positive. Clear?
Yes.
Okay. Now, at this point, at this point, I will get again a point of inflection, but I have to keep it in my mind that from this point to this point, the function is increasing, so the slope would be positive, but and I will get the point of inflection at this point. This point, so the turning point for the derivative will be at this point. Clear? So I will get a curve like this. Some kind of a curve like this. Is it clear?
Okay. Yes.
Then from this to this, from this interval to this interval, from this interval, from this point to this point, and for this interval, the slope is decreasing. I will get the negative uh, f prime of x, and I will get the point of the turning point for the derivative function at this point, right? So I will
Yes.
get a curve like this. Is it clear?
Yes.
Now from this to this, what I will get the, you can say, the function is increasing, so the slope would be positive, and the turning point will be at this point. So I will get a curve like this. Okay, and again for this one the function is decreasing, so I will continue this curve. So finally we graph the first derivative on our concept board. Do you have any question?
No, sir.
Okay, again keep the steps. Now just forget about the purple curve, forget about the purple curve, take um, the point, the green one as your main function. Okay, take it as your green
Okay.
main function and apply the same rules again. And now I am going to change the color into red one. I will choose the red one to graph this function. So what are the conditions now? For the red function, what is my main function? I will look at the green function now. So the condition are same.
Yeah.
The conditions are the same. The turning point of f will be zeros of f prime. Now I will say that the turning point of f prime will be the zeros of f double prime. So the points at which the function is turning, they will give me the turning points of the zero. So you can see the function is turning at this point. So I will get 0 at this point. Clear? The function is
Yes.
turning at this point. right? So I will get 0 at this point. Similarly, I will get 0. The function is turning at this point, so I will get 0 at this point. All these are the point of inflections, the x values. The function is turning
Okay.
at this point, so I will get 0 at this point, and that's it. Now you can see the green function was a function with degree 5, and the red one that I am going to make is a function with degree 1, 2, 3, 4. Clear? Is it clear?
Yes.
Now,
Yeah.
what is the next target? The next target is to find the point of inflection for the green function. So from this turning point to this turning point, it would be in the middle, so probably this point, right?
Yes.
From this turning point to this turning point, it would be in the middle, so probably at this point.
Yes, sir.
Oh,
My
wait.
sister's calling me for dinner.
Hmm?
My sister is calling me for dinner.
Just wait. Just give me 1 to 3 minutes. Let me just check this. I am using
Okay.
another color for highlighting the point of inflections. Okay, I'm taking the blue one. So these are the zeros. Yeah. From this to this, the point of inflection was at approximately at this point. From this to this, it is at this point. From this to this, it would be in the middle. So like this. And from this to, yeah, there is no other turning point. There is no other point of inflection. I will get 3. Okay. Now again, keep the things in your mind. The function is decreasing from this part to this part, right? So its graph will be negative. Clear? But first, we
Yes.
will graph it for this interval. The function is increasing from this red to this red, so I will make a cup-shaped curve, and the maximum point will be at this blue point. So I will get a curve like this, okay, and I have to just take it down. Clear? Okay. Now from this to this interval, the function is decreasing, so again I will get a cup-shaped curve at this point. By taking the minimum value at this point. Clear?
Yes.
Okay. Again, from this point to this point, it is increasing, so I will get a positive function by getting the maximum at this point. So kind of this function, and then it start decreasing, so I will take it down.
Okay.
So this is our f double prime, and this is our f prime, and this one is our source function or the main function. Is it clear?
Okay.
Very interesting.
Yeah.
Okay. Any question?
No, sir.